an organized way to answer questions and solve problems.
The scientific method, go step by step. The scientific method, you experiment. You start with a question, try to find a solution. The scientific method, this is how you do it.
Anyone can think like a scientist by using the scientific method.
ASI, TCI, then state your conclusion. This is the science method. Everyone can use it. ASI, TCI, then state your conclusion. You start with a problem, then end with a solution.
Sally Rod used the scientific method for experiments in space.
A for ask. Ask a question. S for state. State your hypothesis. I for identify. Identify the variables. T for test. Test your hypothesis. C for collect. Collect your data. I for interpret. Interpret your data. S for state. State your conclusion. The scientific method. Go step by step.
All right, everybody. I hope you enjoyed that little bit of a song I shared with you. Let's see. I think my video is showing. So this is my first go around on this pre-recorded video. So let's give it a shot. The first unit lesson that we're really going to get into the content is 1.02. We're going to talk about the scientific method, hence the cheesy song at the start. I like to put in as many things as I can to help you remember the content. So I put a link to that video down here at the bottom. If you'd like to revisit it, I think having things set to music can help us remember. So if you'd like to revisit that, you can. What else are we doing here? Okay, so our objectives, in other words, what are we going to be able to do at the end of this lesson today? I'm going to take some time to read them for you, but I want you to understand that when I say listen, explain the steps in the scientific method, I mean I want you to be able to do that for me when we're done with this lesson. Describe the importance of developing a question, forming a hypothesis in the scientific method, and understand how to design an experiment that tests a hypothesis. That's the whole point of this lesson. Okay. Here's that link again. I don't know why I have it here twice. So the key goal of science is to be able to investigate and understand things that we might not be familiar with. We use these explanations to be able to make predictions about things that we come upon in the future. When you're talking about science, we're only dealing with stuff in the natural world. We collect, as scientists, collect and organize information carefully and orderly so that we can find repeating patterns with things, and also so that other people can repeat our work to find the same conclusion. That's how we double check ourselves. We propose predictions that are testable, and we organize ways of using evidence to learn about the natural world. That's what science is. It's an organized way of using evidence. Before we can get into all of that, we have to understand the difference between basically an observation and an opinion, or an observation and what we call an inference. So experiments begin with observations because you begin by finding a problem that you need to resolve with a solution. The data that you gather from observing the problem can be categorized two ways, either qualitative or quantitative. So qualitative might be how something looks. You would describe it. Quantitative would be something that has a number. Quantitative. So when you're looking at these two words and you're trying to remember, if there's an N, that means number, that means data, like how tall something is, or how long it took to do something, or how many of something. Okay, it always has a measurement component. Qualitative is more subjective, so it's subjective to your own senses. So if something feels or smells or you see a certain thing, that's qualitative, okay? So if you look for something, you could use the L for qualitative. An inference is something that you interpret based on what you come to the situation with. So your prior experience or your or your knowledge you came into the experiment with, right? And we talk about it in general, but that sometimes can be an opinion about something. So we're going to practice this here for a second. Here are some statements, and we're going to decide if these statements are observations or inferences. So if you look here at object A, now those of you who play sports, and even if you don't, you should know that this is a basketball. This is a ping pong ball, or table tennis, and this is a soccer ball. So object A is round and orange. I want you to pause here for a minute and decide if that's an observation or an inference. And I'm going to go through each of these with you and give you a chance to pause. So object A is round and orange. Object A is a basketball. Object C is round and black and white. Object C is larger than object B. Object B is smooth. Object B is a ping pong ball. Each object is used in a different sport. So you need to decide which of these is an observation and which is an inference. I want you to pause the video and take some time to think about that. Okay, you've had a chance to pause the video and make your decisions. What I want you to check your work for is the object A is round and orange. Oopsie. Okay, object A is round and orange. Those are facts that you can prove. That's an observation. Sorry. Object A is a basketball. Well, we're making an inference that that's a basketball because we have previous history knowing that that's a basketball. But it's not what you'd consider an observation. So this is an inference. Object C is round and black and white. That's something that you can see with your eyes. It's an observation. Object C is larger than object B. That is also something that you can see, you can prove. That's an observation. That's right here. Object B is smooth. That's also an observation. Object B is a ping pong ball. That's an inference. Again, you're using your previous knowledge of playing ping pong to understand and recognize that as a ping pong ball. And then each object is used in a different sport. You could argue that both of those are observations you could make by watching those sports, and inferences if you already know what these balls are. So, observation and inference practice. Here's another example. There is steam coming off of the coffee cup, and the coffee is hot. So you need to decide which is an inference and which is an observation. So go ahead and pause the video, make a choice, and then we'll come back and talk about it. Okay, you should have had time to pause the video and make a choice. If there is steam coming off of the coffee cup, that is something that you can see. That is an observation. So the steam on the coffee cup would be an observation. You're inferring, because you see steam, that the coffee is hot. So you are using your prior knowledge that when things make steam, those things are hot. So that's an inference. So number 1 is observation, and number 2 is inference. If you checked the temperature, and you said the temperature of the coffee is 120 degrees, that would be an observation. Still not an inference. You could say it's hot because it's 120 degrees, but that's an inference. Okay, someone tells you it's cold outside. What evidence is going to make you believe this? Keep your responses to single words or simple phrases. So pause the video here, write a few things down, and let's check your understanding when we come back. Okay, you've had a chance to pause the video. Let's take a look at what this picture is showing us. What evidences do we observe that would make us believe that this young woman is cold, that it's cold outside. You could say, I can see her breath, right? So that usually we infer from that because her breath is hot and the air is cold, it's making a fog. You could say shivering. She appears to be holding herself and shivering, which is the body's response to being cold. You could say like hat or scarf, because those are items of clothing that you'd wear when it's cold. So I know that sounds simple, right? But you do this all of the time. All right, finding evidence. So here's what we have to be careful of. You notice that everyone at school is wearing blue on this one day. So you infer, okay, well, everybody's favorite color must be blue. How would you go about proving that? That would be a complicated task. So in order to go about proving that, you would have to survey every single person at the school who's wearing blue. And then you would have to assume, or I should say, your hypothesis would be that everybody's favorite color is blue, but you'd have to prove that from examining the data in your survey. So can be a complicated process. Chances are your inference is incorrect. It's probably not that everybody's favorite color is blue. It's probably like Spirit Week, and they're supposed to all wear the same color. All right, explaining and interpreting evidence. So what we do when we begin an experiment is to make an explanation for what we think is happening. We call it a hypothesis. We use a controlled experiment where only one variable is allowed to change. You have to keep everything else the same in the experiment, or you'll be testing different situations. So what we call the independent variable is the variable that's changed by me, the scientist. The dependent variable depends upon what's happening with the independent variable. That's the variable that I want to watch. Okay? Controlled variables are all kept the same. So here's a situation. You want to test how tall a tree grows over time. The independent variable is the time. I'm going to watch the time for a certain length. Okay? That's not going to change. I mean, it's going to change because time changes, but time is not dependent upon anything else. The growth of the tree, usually in height, okay, is what we would observe over time. And that height of the tree is going to depend upon how much time I watch it. But I want to keep the variables, all the other variables, the same in this experiment. So I would want to take like 2 trees and put the same soil and the same amount of water and the same amount of sunlight and the same amount of time, because if I change any of those variables, I might be affecting my experiment. You're going to want to gather more data. You have to understand that just because you make a hypothesis at the beginning doesn't mean you have to be right. That's the great thing about science. You can be wrong and not, and as long as you explain why you're wrong, you're still doing science appropriately. So there are groups of scientists that analyze, review, and critique each other's work when they're doing data research, right? So it's okay to be wrong. You just have to explain why you were wrong, and then what you have to do is change your experiment to make it right. So designing an experiment, here are the steps. You're going to need to know these, okay? The thing is, depending on where you look, you'll find various numbers of these steps, but here are the 7 steps, and that's, pretty much all you're going to find. You're going to state the problem. You don't do an experiment unless you need to, okay? So you state the problem, and then you form a hypothesis. Like if the hypothesis is a brief explanation of why you think there is a problem. You set up a controlled experiment. You record the results of your experiment. You look at the results of your experiment, and then you draw a conclusion from what you can prove or see and observe from your experiment. And then you can publish your results. Now, this process might repeat itself several times in order for you to get it to a point where you're verifying your hypothesis. So an experiment can evolve. Just remember that it's an ongoing process. And you should, as a scientist, you should always be asking questions, observations, making those inferences, and testing hypotheses. So some challenges to experiments are ethical considerations. So we can't always test things on humans because it's not safe. There are a lot of variables out in nature, so we think we're looking at why something's happening, and we don't realize that it's because of a variable we're not even taking into account. Also, you want to make sure, in order to make sure that a scientific experiment is valid, you want to make sure you do it on a lot of different subjects. So there might not be enough subjects to make your experiment valid. If you do an experiment on 3 people and there's 7 billion on the planet, probably not, you're not going to be able to test all 7 billion. Writing a conclusion is going to be a big component of your job here in the science, in biology. If I ask you to write a conclusion paragraph, you're going to want to save this part or write these down. Your conclusion paragraph is going to have to state your hypothesis. So whatever prediction you made at the beginning, we're going to talk about how to make those more, make a hypothesis statement more clearly in class. You're going to have to decide whether or not your data proves your hypothesis or not, and then what were your findings. So back that up. So the experiment was that if you soak gummy bears, so let's see, here's the problem. My gummy bears got wet and they got all big and squishy. So that's a problem because I like small and chewy and not, great big swollen gummy bears. So my problem is my gummy bears got swelled up. The experiment will be, well, I hypothesized that my gummy bear would dissolve in the water. Okay, so I'm not sure why my gummy bear got swallowed because I would assume it would dissolve in water. So that's my hypothesis. Gummy bear is going to dissolve in water overnight. Okay, I soak my gummy bear in water overnight, and my hypothesis was partially correct. When I took the gummy bear out of the water had turned a pinkish color, so you could see some of it got dissolved. Also, when I tasted the water, it tasted like a strawberry gummy bear. So that leads me to believe that some of my gummy bear dissolved in the water. What I was most surprised to see was that the gummy bear grew in size. Gummy bear's width increased by 2 centimeters, and the height of the gummy bear increased by 4 centimeters. This leads me to believe that the gummy bear soaked up the water, and this allowed it to expand, resulting in a larger gummy bear. This is an excellent conclusion paragraph, because if you notice, it lists the hypothesis. I hypothesized that my gummy bear would dissolve in the water. So if I soak a gummy bear, then the gummy bear will dissolve in water, right? It says whether or not, or in some fashion, my hypothesis was correct. I explained what I did in the process, or what I should say I observed during the process, that leads me to believe that it was partially correct. And then I also listed the things that I learned, right? What I was most surprised to see, right? And then I actually put in some quantitative numbers, data, right? So there is quantitative data here. 2 centimeters and 4 centimeters are numbers. Qualitative data, the way that it tasted and what I saw in the color, okay? And because of both of those being present, it's more valid. And then I concluded it with, it leads me to believe that gummy bear soaked up the water, blah, blah, blah. So this is a really good conclusion paragraph. When I ask you to write one, it's going to be something like this, and we'll have a chance to practice. All right, fastest route to school. Take a minute and read through this. Pause the video if you want to. I'm going to leave you with a theory. It's a well-tested explanation, okay? It's supported by many, many scientists and many, many, many experiments over a long period of time. We're not saying it's a fact. We're saying it's a theory that is supported. It can be proven wrong if somebody decides to do an experiment we haven't thought of yet. But matter is made up of atoms, cannot be destroyed or divided. Elements are exactly alike. Atoms are exactly alike. The evolutionary theory is controversial, but understand that it is backed up over many, many, many experiments by many, many, many scientists over a long, long, long period of time. So maybe in the future, if we find another way to test it, then we'll be able to disprove it, but evolutionary theory is supported. This is just a cute little meme of the scientific use of theory versus the casual use. So in order to be a scientific theory, it has to be fortified by facts. It has to have examples you can find in nature, and it has to have a lot of research. Okay? Casual use of theory is just a hunch. It's an opinion, educated guess maybe. Okay? Okay, so here are those standards again. I want you to stop and think about how you feel. Do you think that you could ace a quiz on this stuff? Are you going to go and review the material? If you have a question, you're going to write it down and ask in class. I'm going to read the text and use Quizlet. Now D, I'm going to explain more about this in class. So make sure you at least watch the video from today. Okay, thanks guys. Talk to you later.